And I have started recording. All right, just gonna end the polling, sharing the results. So looks like people are feeling okay about the summer. That's good. It can be a lot really fast. Yep, so a lot of people plugging away with school. That's good. I like that people are on pace to be completely ready for the exam. Whatever I can do to help, I am happy to do. So we can discuss that. And yes, all right. I'm glad to see that people aren't in a big, there's a word I'm looking for. I'm not sure it'll come to me. A big crisis, life crisis, trying to manage this course and whatever else is going on. I don't want you to be in crisis. So it is a far better thing if you're able to manage it all, relax a little when the time comes. I don't know if people are able to watch the Olympics at all, or watch a movie or read a book or something. Life needs some balance. All right, so a couple of things that were at the end of the PowerPoint last time that I didn't dig into, I think because I thought they were short of the chapter 14 homework or beyond the chapter 14 homework, but I wish that I had continued on a little bit more. So we did talk about this mechanical equivalent of heat, and that Joule set up an experiment where water would get stirred by a process that was a change in gravitational potential energy, and that conversion of gravitational potential energy into this stirring energy addition to the water caused the water to heat up. And so there's this mechanical equivalent of work. And so the idea was that the mechanical equivalent of heat, 1 calorie, is 4.186 joules. And it's the idea of how much energy, heat energy, it takes to change the temperature of water from 14.5 degrees Celsius to 15.5 degrees Celsius. Now, it turns out water is a particular unique substance. Other substances have different, what we call heat capacities. So we see the heat is the energy transferred due to temperature differences, and we have a relationship for that. But heat and internal energy, heat is energy that flows from a high temperature object to a lower temperature object. When something absorbs heat, its internal energy increases. And when something releases heat, its internal energy decreases. And I'm sitting here drinking my ice water. Oh, this camera. Sitting here drinking my ice water, and I think about this stuff all the time, internal energy changes and all that. Now, 2 things can happen when something, that should be absorbs or releases heat. So when the water that went into my freezer lost heat, it cooled down to its freezing point. Water freezes at 0 degrees Celsius, and then it underwent a phase change. It went from liquid water into solid ice. And so we can talk, we can kind of focus this discussion around the idea of water because it's ubiquitous and you're familiar with the phase changes that, you know, solid ice, liquid water at 100 degrees Celsius transforms into gaseous steam. So this world where heat is added to a substance works with a lot of different substances, but let's think about water for the time being, because that's one that we have some very good experience with. So when a solid or liquid of mass m absorbs and no phase change occurs, then the equation we have is Q equals mc delta T. M is the mass of that substance. C is the heat capacity of that substance. And delta T is the change in temperature. And as always, you're in better shape if you convert from Celsius to Kelvin, because you can never go wrong. But if we have delta T, the degree size for Celsius and Kelvin are the same. So the temperature difference between, you know, 70 degrees Celsius and 20 degrees Celsius is the same as the temperature difference if I converted those into Kelvin. So heat capacity is a physical property that relates to how energy absorbed reflects the changes in temperature for the substance. Water, this ubiquitous substance that we have on Earth, has a pretty, really high heat capacity. You add a lot of heat to water before the temperature increases. Other things have a smaller heat capacity. So without trying to get into all the different things, we'll have a table coming up. But there are two specific areas where water at 0 degrees Celsius, this is when it happens at 0 degrees Celsius. So we can remove heat from water and it will get colder and colder and colder. It will be cold water until it's at 0 degrees Celsius. And then when we continue to remove heat from it, it will turn from cold liquid water into solid ice at 0 degrees Celsius. Likewise, if we're adding heat to water, it will just become hotter and hotter water up until we reach 100 degrees Celsius, at which point when we add more heat, that liquid water will undergo a phase change and turn into gaseous steam. So the equation here is Q equals mL. L is standing for, capital L here, standing for the latent heat. And there's two things that we're talking about here, latent heat of fusion. So it would be L with a subscript F, and that fusion turns into a solid, or from a solid into a liquid. And then vaporization turns into a gas, so L sub V, or from a gas back into a liquid. So if you were having fun watching what happens as you add heat to liquid or to water, as you add heat to water, if I start off with ice at -20 degrees Celsius, When I add heat to the ice, I will get warmer and warmer ice. Ice can have a range of temperatures. Generally, our freezers are something like -20 degrees Celsius, so that's probably a typical. And when we're adding heat, Q equals MC, the heat capacity of ice, which is different than the heat capacity of water, times the change in temperature. We have a temperature range here, -20 degrees Celsius up to 0 degrees Celsius. And I could figure out how much heat I added if I knew the mass and I had the heat capacity for ice. And then something weird happens. At 0 degrees Celsius, I add heat and the temperature doesn't change. From this point to this point, I'm adding heat, but the temperature is staying the same. And when I'm adding the heat, it's Q equals MLF at 0 degrees Celsius. At 0 degrees Celsius, I add heat in order to undergo a phase change from solid ice to liquid water at 0 degrees Celsius. It will stay at 0 degrees Celsius that whole time. So my ice water here is at 0 degrees Celsius because ice and water are coexisting. And even as this glass absorbs heat from the room, and my fingers holding it, even as it absorbs heat, all that heat is doing is causing a phase change of the solid ice into liquid water. And once all the solid ice disappears, then it will start warming up. That warm up phase, Q equals MC, heat capacity of water, delta T. So that's how much heat I need to add in order to warm up my water. If I want to warm up my water all the way to its boiling point, then there I go. And then Q equals MC of, nope, sorry. Oh, I lost my mind. MLV. Oh, I stink at using the eraser thing, but I think I'll try to. Now I gotta get it back into writing mode. I'm still on eraser. Shut off the eraser. Okay, Q equals MLV. So it's the mass of the water that I have at 100 degrees Celsius, its boiling point, times the latent heat of vaporization to convert liquid water into gaseous steam. And then if you've ever had a really bad burn, you've probably had superheated steam. Steam can be hotter than 100 degrees Celsius. And you can have superheated steam and get a wicked bad burn. So be careful about that. So here's a table that lists the melting point, so the temperature at which the phase change would take place, and the latent heat of fusion for that temperature. And then at the other end, the temperature at which the phase change from a liquid to a gas would take place, and the latent heat of fusion there. So water that we're familiar with, the melting point is at 0 degrees Celsius. The latent heat of fusion is 3.33 times 10 to the 5th joules per kilogram. Then again, at the other end of the spectrum, once you heat it all up to 100 degrees Celsius, the latent heat of vaporization, the energy it takes to convert liquid water into gaseous steam, is 2.26 times 10 to the 6th joules per kilogram. And then all sorts of other substances, obviously like metals, that temperature at which they turn into a solid metal, or conversely, when they would turn into a liquid molten metal, is really high. It's a really high temperature. Whereas some things like liquid helium and liquid nitrogen are very, very cold. And here's the temperature at which they have to be to liquefy. Likewise, it's a pretty cold temperature for them to boil and turn into gases. So there you go. Okay. So there were some questions from the homework that I think would have been extra confusing because we didn't get this far into the lecture, and I apologize for that. Hopefully the homework videos helped walk through these concepts in a way that made some sense, but we will take time before the quiz today to go over questions that you have. But when we're transferring heat to raise the temperature of the water inside an aluminum pot, we also have to heat up the aluminum pot. So we need the heat capacity of aluminum and the change in temperature, 30 degrees to the boiling point of water. So the 70-degree temperature increase in temperature there. And then we want to boil away some of the water. So we also have to account for the latent heat of vaporization. These kind of problems are multi-step. You can't do it in just one equation, bang, there it is. You have to take each thing and it's kind of a pain. So for the aluminum there, Q equals MC aluminum delta T for the aluminum. So 0.750 kilograms times the heat capacity of aluminum. I think that's 900 joules per kilogram degrees C. And then the change in temperature, all the aluminum did was increase in temperature 70 degrees Celsius. So we get a number for the aluminum. Then we get a number for the water, what it took to bring the water up to its boiling point. Again, 2.5 kilograms of water. The heat capacity of water, 4186 joules per kilogram degrees C, and the same 70 degrees Celsius for the water. But then we're not done, because we also need to phase change 0.75 kilograms of water. Q equals MLV. So 0.75 kilograms of water times the latent heat of vaporization of water, which I forget, it's on the previous slide, but it's a big number. And then we add all three numbers together to get how much energy was transferred. And then if it's 1 joule per second, we can figure out how many seconds. But we'll go over that in more detail if people have questions at question time. So specific to lab, and I think another one of the homework questions is the world of calorimetry. If you had general chemistry before taking this class, Typically in general chemistry, you'll do something called coffee cup calorimetry, where you will ignore the heat capacity of the container because it's a coffee cup, and just kind of have a simplified version of figuring out what the heat capacity of your unknown object might be. For us, we can know the heat capacity of a container. The container that we would typically use in lab is an aluminum cup inside an insulated cylinder. And so all we're doing here in calorimetry is saying, okay, if I have an object whose heat capacity I don't know, and liquid water surrounding it, and then an aluminum container holding that water in place, I can know how much heat flowed from a hot object into my room temperature water and my room temperature aluminum jacket, and figure out, once the temperature equilibrates, how much heat the object lost in order to heat up the other things. And then if I know the mass of that object, I have all the information I need to figure out the heat capacity of the object. So typical calorimetry problem, we have an unknown object, some mass, heated to a known temperature, say 90 degrees Celsius, then placed in a thermally isolated container, that's our calorimeter, containing a known mass of water, and we know the mass of the container as well. Once it reaches that final temperature, we're able to figure out how much heat the water gained, and then how much heat the object gave to it, and we can figure out what's going on there. So that's heat capacity. Some typical specific heats, water 4186, ice about half that, 2090, and then aluminum was the 900. I did remember that. Okay, and so our 80,000 liter swimming pool increased by 1.5 degrees Celsius, so we would have to get that, since our heat capacity for water is 4186 joules per kilogram. We would need to figure out how many kilograms 80,000 liters of water is, and then we can figure out the heat transfer. So density of water is 1,000 kilograms per cubic meter. There's 1,000 liters in a cubic meter. And so we can figure out the mass of the water and then do the Q equals MC delta T. So we have the delta T, we'd have the M, and the heat capacity is 4186. But we can do that at question time. So my apologies for not getting all the way through that part of lecture. That was, I don't know why that happened. I think I thought this was all going to be part of the next thing. Okay, I got to find our Canvas page. And for reasons that I'm not sure of, I'm not seeing it. I'm getting there. All right. I will be very interested to see how fall 2021 plays out in reality. I thought Salem State took a pretty bold move requiring everyone to be vaccinated, and then but they were also announcing that everyone had to wear masks, and I thought that was kind of a big ask for everyone to be vaccinated and to be wearing masks. And then they updated that guidance to say that no, people didn't have to wear masks. And now things seem to be changing in transmission of the virus, that more and more places will have to be wearing masks. So I just don't know what's going to happen in the fall, but we'll burn that bridge when we get to it, as the saying goes. So we will spend some time going over chapter 14 stuff before the chapter 14 quiz. We have labs on heat capacity and the ideal gas law. The heat capacity lab, there's a video of me kind of doing what you would have been doing if you were in lab. There's a phys guide to kind of go through some of the concepts for you. And then the questions are based on what the questions would be in lab. So just a couple of calculations for you to figure out the specific heat of a metal given some information. So that is pretty straightforward. And then the ideal gas law lab is a this PhET is HTML5, so it is updated from the what would have been a program that wouldn't work for you. But you can pump in some air molecules. You can read what the pressure is. You can heat it up and see what happens at a higher temperature. You could expand the volume of the container or squish the container and see what happens. And it's all this relationship between pressure, volume, the number of molecules, and the temperature. And you can read all of that. And then the questions I have for you are questions you could do without playing with the PhET. So I have it there to kind of enhance your experience, but it's PV equals nRT kind of questions. So, and do not forget that temperature should be converted into Kelvin when you're doing the ideal gas law. Okay. No. So, in the course of human history, somewhere around the 1800s, scientific theory and engineering, not necessarily choo-choo train engineering, but engineering to turn theory into something that actually works, coincided to the point that steam engines could be built. Now, a steam locomotive engine was something that was designed that could transport human beings at speeds 60, maybe 70 miles per hour. Really, really fast. And there was some debate at the time whether a human being could survive traveling at that speed. It sounds a little silly now, but maybe right now we're saying, gee, I wonder if a human being could travel at the speed of light and survive, or at 3/4 of the speed of light, as we contemplate maybe traveling from one planet to another. How fast physiologically can human beings move before something weird happens to them and harm befalls them? So this struggle, ultimately it turned out that human beings could travel that fast without suffering ill physiological effects, but it was a question that people had. That was the cutting edge of engineering at the time. I think when I first made this slide, the Salem power plant was still a coal-fired power plant, but the idea was that you shoveled coal into a furnace boiler, that boiled water turned it into steam, that steam was used to turn a turbine that produced electricity for the city of Salem, Massachusetts. Now it's not a coal burning plant, it's a natural gas burning plant that does exactly the same thing. Nuclear power, right after I graduated from college, I traveled to a country that was at the time the Soviet Union. And in the Soviet Union, the university that I stayed at, piping hot showers. You went in and you took a shower and the water was so hot. And then, like the second week I was there, it was only cold showers. And I asked what was going on, and well, it turns out that the nuclear power plant was in shutdown mode for maintenance and repairs. Okay. And it turns out the hot water that was pumped throughout the entire city, including the university, was the wastewater from the nuclear power plant. Now, the nuclear power plant or the power plant in Salem, Massachusetts, the waste that they generate, besides, any kind of, smoke or air pollution or something like that, the waste that they generate is typically in the form of heat. There's waste heat that they have to get rid of somehow. And nuclear power plants and other kinds of power plants, that waste heat is dumped into hopefully a convenient body of water. So the Salem power plant, you'll notice, is right in the harbor. Power plants, nuclear power plants, other power plants, if you ever notice where they're built next to a body of water. And it takes someone who's into ecology to appreciate that the waste heat that is dumped into the local body of water, the problem is that it's changing the local ecology. When the temperature is typically cold and then you dump waste heat, things warm up. This idea, this heat engine, a region of high temperature and a region of low temperature, and harnessing the desire of heat energy to flow from a high temperature region to a low temperature region in order to do work is how heat engines are designed to work. Now, we have heat engines that work in reverse. That would be a refrigerator or an air conditioner. And we have heat engines that work in this way that we're talking about. Say your gasoline-powered automobile, it has to dump waste heat into the environment, and you have a radiator that releases that heat to the outside. So this is the idea of heat engines. That's how a lot of our technology, even right now, still works. There's some other kinds of ways of generating power, but for the most part, what we're using is heat engines. So internal energy is related to the temperature of a gas. We covered that in our last chapter. Work, for our purposes, is going to involve lifting something against the acceleration due to gravity to some height. So we'll just say work is mgh. There's some other definitions of work that we talked about in Physics 1, but for right now, we can go with this very simple definition. And then Q is heat, and it's related to the temperature, but we can store heat in an object as is accounted for in heat capacity. And I think this is where I messed up with the previous lecture, because I knew we'd be talking about heat capacity, so I didn't feel the need to cover it then. But here we're using heat capacity. So we're going to have some things that are positive and some things that are negative. So when a system gains heat, we'll say that that heat is positive. When a system loses heat, we'll say that heat is negative. Likewise with work, if the system does work, that's positive work. If work is done on the system, we'll say that that's negative work. What's the system? Well, it's a container that has a gas in there. That gas will be our working gas. It will either do work or have work done on it, but the work is there. This container is of a fixed volume, but we can just see the very simple definition that if I have a gas trapped in a container at some initial low temperature, it has a certain internal energy. And if I add heat into the system, my final internal energy is going to equal whatever my initial internal energy was, plus the amount of heat that I added. I'd have another calculation step if I wanted to figure out what the final temperature of my gas is. But for right now, like I have this accounting for energy, add energy, new higher energy. It's going to be useful to us. For the work part, I would have my gas trapped under a piston that is able to move. And at my initial internal energy, pressure, work, everything is kind of balanced out. But if this internal energy was enough to do work related to the pressure, it will apply a pressure force that lifts up this gold brick. And now that it did work, my final internal energy of the gas is lower by the amount of work that the gas did. So it's kind of keeping track of energy again. So it's all energy. So the first law of thermodynamics, remember that we had a zeroth law of thermodynamics that was needed because they were so excited to do the laws of thermodynamics and match them up with Newton's 3 laws that they skipped the part where we could actually take the temperature of something. And that's pretty important for thermodynamics. But the first law of thermodynamics, and it can be written in a few different ways, but it's this conservation of energy is ultimately the idea. That heat minus work is going to be the change in internal energy. And so that's Q minus W equals delta U, or delta U equals Q minus W is the other way we sometimes see this written out. I think that's coming up on the next slide, so I won't bother drawing it. There was a time when I would cart a projector into class, and that would just be sitting on a table. And when that was the case, I would sometimes take the projector and turn it at an angle so it looked like the person was running uphill. Only because we just said that work is going to equal the change in gravitational potential energy. And in order to have this person's gravitational potential energy increase, she'd have to be running uphill. Anyways, this is just a way of kind of picturing the person is having some kind of workout, so they are emitting heat. The system is losing heat. Q is going to result in heat loss to the environment. They are doing work. And so they are experiencing a decrease in internal energy. Metabolic internal energy. They will probably want to eat some food in order to restore their energy. All right. Nothing works in reality in an ideal process, but if it did, if there was no energy loss due to friction of the piston with the walls of the container, I could plop my gold bar on top of my gas that is trapped inside a vessel underneath this piston. As the gold bar dropped down, work would be done on the system in order to conserve energy. The system would lose heat into the surrounding water bath, but then it could reabsorb that heat from the surrounding water bath and have the gold bar go back up to exactly where it began. This would be an idealized reversible process where there's no other form of energy loss than just what we have: heat, internal energy, and work. Now, we know that that doesn't really work, but stick with me. Okay, so we have a gas under pressure. The volume of the container increases as the gas pushes on the piston. And so we have P times a change in volume. P delta V is going to equal work. So here is a pressure volume diagram, your first PV diagram. There are going to be several others. The area under the curve here, since it's not really a curve, just a block, is base times height, right? So P delta V, constant pressure. So we have a way of figuring out how much work is done. The work is shaded in purple. There's all sorts of funky things that can happen. This one isn't so bad. It's just kind of a square on top of a triangle. We could figure out this area if we wanted to without too much effort. But then there's all sorts of crazy shapes that can happen, and that would be the job of calculus, which is why Isaac Newton either invented or discovered or co-discovered calculus. Okay, Adding heat to a system of constant volume, you have an initial pressure, you add heat, so you've increased the internal energy of the gas, therefore it's pushing harder against the walls of the container, and there is a larger pressure. We don't need to do that. We don't need to worry about this yet. I'm coming up to a set of equations to that those things kind of illustrated. There are some thermodynamic processes and their characteristics. For constant pressure, then we have a number, a value for the pressure, and work equals P delta V, or if we want some other insight using the first law of thermodynamics, first law of thermodynamics is change in internal energy equals Q minus W. So this is rearranged to say Q, the heat for a constant pressure process, is the change in internal energy plus the work, P delta V. Now, for constant volume, since we're saying that work is mgh, we're lifting something up, we're expanding our vessel, for constant volume, no work can be done because the volume isn't changing. So work by necessity equals 0, but if we add heat to the system, we're increasing the internal energy, temperature, of that gas. Isothermal is a condition where we're saying the temperature has to be constant. Well, if the temperature is constant, then the internal energy isn't increasing. So the first law of thermodynamics reduces to just work equals Q. If I add heat, the system does work. If I remove heat, the system has work done on it. And then adiabatic is a term for when there is no heat flow. And if there's no heat flow, then Q is the heat that's flowing. That has to equal 0. And so work equals negative change in internal energy. We don't have to do heat capacities at constant volume and constant pressure, because that's just weird. But we will talk about heat engines then. We're using all this information that we have to build these heat engines. The characteristics of a heat engine, the theory behind how a heat engine works, is you have a high temperature region. So for a power plant or a steam engine, that's the boiler. It's typically at around 100 degrees Celsius to boil the water, turn it into steam. Heat is extracted from that high temperature reservoir, and it does work in some sort of engine. That work is removed from the system. When you remove the work, you're decreasing the internal energy of the gas involved. Therefore, it's at a lower temperature. Truly, you want to lower it down to when it's like a liquid water again. So you dump that waste heat into a cold temperature reservoir and then recycle it in the system. So this is the basic idea of a steam engine. You boil the water in the boiler, turns into steam. That steam is at a lot of energy, so high pressure. It pushes the piston out, which through a series of gears and other things makes the wheels on the train go around in a circle. It now is at slightly lower temperature when there's something exposed to outside air, general room temperature or standard atmospheric temperatures. The steam will condense back into liquid water that will get pumped back up into the boiler, and the boiler will produce steam again. So this is the basic gist of turning heat into work. So here is the idea of one form of a heat engine and the efficiency of it. is going to be the amount of work that gets done versus the heat that was extracted from the high temperature reservoir. And you will find that the efficiency of heat engines is pretty terrible. This would be our ideal maximum efficient engine, and that would be at 24%. So heat engines are notoriously very inefficient. We are able to make heat engines work in reverse, to have a cold temperature reservoir that by doing work on the system dumps heat out of it. So this is how the refrigerator in your house works. You plug it into the wall, there's a motor. That motor is condensing a gas and then letting it expand. When the gas expands, it cools, and there's cooling of the inside of your refrigerator, but you are dumping waste heat into your kitchen. That waste heat is the heat that is removed from inside of your refrigerator, plus extra heat from the work that was done. So it is very inefficient to stand there with your refrigerator open. If you had hopes of cooling off your room, you will not be cooling off your room by leaving the refrigerator open. Likewise, if you have an air conditioner, you will notice that a wall unit air conditioner or window unit air conditioner is stuck in a window such that there's inside and outside. You are dumping extra heat beyond just what you're removing from your room into the outside environment. If you just stick window unit air conditioner on your kitchen table and plug it in, the net result would be warming up the room. You need a region of cold temperature and a region of higher temperature. And a heat pump, same kind of deal. We've spoken about it already, that heat will flow from a region of high temperature to a region of low temperature spontaneously. And then you have to put work into it to get it to go the other way. This is ultimately what is called the second law of thermodynamics. When two objects of different temperatures are brought into thermal contact, heat will flow. Why? Because they're different temperatures and they're in thermal contact. The second law dictates that the spontaneous flow of heat will be from the high temperature region to the low temperature region. Spontaneous heat flow never proceeds in the reverse direction. We can put work in and get heat to flow the other way, air conditioner, refrigerator, but that's not spontaneous. That requires work. But spontaneous heat flow is from high temperature to low temperature. And if we set up the engineering in a way we can harness that natural flow of heat from a high temperature region to a low temperature region to get it to do work for us. So this is kind of related to entropy. My sister-in-law was the first person in the family to get a PhD, and she was very disappointed. She spent, all her time working on a PhD, and then she got her degree and it just said Doctor of Philosophy, which is what PhD stands for. But she was a scientist and she didn't want to be a philosopher. But there's a philosophy aspect to this concept of entropy. Things tend toward greater disorder. If I take an ice cube and set it on the table, it's solid ice, which is a highly ordered state. But as the natural flow of energy goes into that solid ice, it will turn into liquid water, which is less ordered, more of a mess. The solid structure versus liquid, less ordered. If I let that water sit there on the table, some of that liquid water at room temperature will jump into the gas phase. There's a vapor pressure layer on top of the liquid water, and some of that will move about the room, even less ordered. So entropy is a measurement of mass, a measurement of disorder. And so the term for entropy, delta S, is Q, the heat flow at a given temperature. So Q over T is the entropy for a condition. Entropy is not conserved. We talked about energy being conserved, but entropy is not conserved. If the amount of heat flow from our high temperature reservoir to our cold temperature reservoir is 1050 joules, then what we have is an increase in entropy. Entropy is always increasing. We're tending toward more and more disorder. The efficiency mentioned briefly before, it is 1 minus, this is supposed to be over, TC divided by TH. We'll try to fix that sometime. Sorry about that, but you can see it in the textbook as well. But TC divided by TH. And then the work that's done is the efficiency times the heat extracted from the high temperature reservoir. Clear. And then just some other things. Okay. Ooh, those are the laws of thermodynamics. You guys are, oh, let me just, the third law of thermodynamics. There's this thing that we call absolute zero. Absolute zero cannot be reached in a finite number of steps. So we've gotten pretty close to 0 Kelvin, but we haven't achieved absolute zero in any laboratory experiment. So that is that. And I opened this up multiple times. That was less than ideal. So when you go to do the chapter 15 homework, there's a bunch of equations here spelling out the first law of thermodynamics, efficiency, maximum efficiency, entropy. So when you tackle the homework, there's questions on efficiency, conservation of energy, and entropy. I think you're okay for the chapter 15 homework. What will be as important, more important as you look forward to next week, you will see the practice exam. Do spend a little bit of time going through the practice exam questions, particularly as they relate to thermodynamics. So here's a step. We have those 4 conditions that we talked about, whether something is at constant pressure, constant volume, constant temperature. So as you consider going from A to B, this is a graph of pressure versus volume. Therefore, from A to B is all at the same volume. If the volume isn't changing, then we know some information about work, because work requires the volume to be changing. From B to C, we know that this region, this horizontal line, is at constant pressure. So there's some information we have about constant pressure. C back to A. All bets are off, everything's moving, pressure and volume, but the volume is increasing, so it's doing positive work. Pressure is increasing, so that thing must be gaining a bunch of heat. So then we have some information. It's kind of like a Sudoku puzzle or something. We have some information and we have to fill in the rest. And that's a typical kind of question that you would have on a heat engine. So spend some time working on the practice exam before Thursday this week, because we'll have time on Thursday to go over any questions you have on chapter 15 homework before the quiz, but also on the practice exam. Just because I figure next Tuesday is exam number 1, 1 week from today is exam number 1. And if you work through the practice exam trying to answer those questions and then can ask any questions you have this Thursday, then as you study for the exam over the 4 days between Thursday and Tuesday, you're just in a better place, I think. If you've already tried to answer it and had some questions answered and then can work on it some more. Obviously, if you don't get that far by Thursday, it's understandable. Do spend the time before 1 week from today, Tuesday, going through the practice exam questions and chapter 15 homework, all of the homework. So you're ready for the quiz. Okay, we have reached that point where if you have any questions from the chapter 14 homework, it is a good time to go over them. So mass. All right. So we did have a question on number 1 that came earlier. I have chat open. If you have questions, fire away. But number 1, 80,000 liters of water. We do our density of water in kilograms per cubic meter, but it turns out that water also has a density of 1 kilogram per liter. And we saw that in one of our earlier labs. So 80,000 liters is 80,000 kilograms of water. And we want to figure out the heat transfer during this heating. Q equals MC of water, delta T. So we have 80,000 kilograms of water times a heat capacity of 4186 joules per kilogram degrees C times a change in temperature of 1.5 degrees Celsius. So the heat that is transferred in that event, 80,000 times 4186 times 1.5. I'm jumping into scientific notation on my calculator because it's a huge number, 5.02 times 10 to the 8th joules of heat transferred. Clear, close. So number 13, I need to check the latent heat of vaporization for water is 2.26 times 10 to the 6th. So, 2.26 times 10 to the 6th. Don't forget it. LV water. 2.26 times 10 to the 6th joules per kilogram. Okay, so we have an aluminum pot that we are ultimately going to increase in temperature from 30 degrees to the boiling point of water. I fear that that was not clear in the phrasing of this question, but we are not going to boil our aluminum pot. We're going to boil our water. So heat pot, Q equals MC aluminum delta T. So the mass of aluminum, 0.750 kilograms, times the heat capacity of aluminum, 900 joules per kilogram degrees C, and it's increasing. Delta T is going to be the final temperature, 100 degrees Celsius, minus the initial temperature, 30 degrees Celsius. That is 70 degrees Celsius. So the amount of heat that it takes to heat up our pot, 0.75 times 900 times 70 is, I never know whether to stay in scientific notation or not. But we'll do 47,250 joules. That's how much heat it takes to heat up the aluminum pot. But wait, there's more. We need to heat up the water. Now this is liquid water that we're heating up to its boiling point. Q equals MC water delta T. So the water, there's 2.5 kilograms, 2.5 kilograms times the heat capacity of water, that's 4186 joules per kilogram degrees C, times its change in temperature, 70 degrees Celsius. So that one is a lot bigger a number. Not only is 2.5 bigger than 0.75, but 4186 is a lot larger than 900. So 4186 times 70 degrees Celsius. So that number isn't 47,000, it's 732,550 joules. It's a lot of energy. And now we want to boil phase change, 0.75 kilograms of water into steam. So that's Q equals MLV, latent heat of vaporization for water steam, takes place at 100 degrees Celsius. So that's going to be 0.75 kilograms of water at the 2.26 times 10 to the 6th joules per kilogram. So 0.75 times 2.26 times 10 to the 6th. It's 1.695 times 10 to the 6th joules. What a mess. That's supposed to be a 1. It's 1.695 million joules there. So add them. That's how much energy it took at each place. 1.695 times 10 to the 6th plus 732,550 plus 47,250. Was that it? I get 2.4748, 2.47 times 10 to the 6th joules. And then I'm going to add this at 500 watts. 500 watts is 500 joules per second. So that's 2.47 times 10 to the 6th joules. 500 joules per second is going to be 1 over 500 seconds per joule. So joules will cancel. I could divide it by 500 joules per second, or I could just set it up this way, but I'm just taking that number and divide it by 500. And I'm getting the number of seconds, 4.95 times 10 to the 4th, nope, third seconds. So that's 4,900 seconds. So if I divide by 60 seconds in a minute, I'm going to get, divided by 60, 82 minutes. And I could convert that to hours if I wanted to, but that's number 13 in all its glory. Other questions that people have before a quiz on chapter 14 material? I am seeing none. I'm going to stop recording.